All right, Tommaso, shall we start?
Yeah.
It's a great pleasure to introduce Tommaso de Fernex, who will tell us about Motivic integration on Berkovic spaces.
Well, thank you so much for the invitation, and it's very nice to be here on Zoom. So I want to talk about this is a work in progress with Chunqing Lao, and we hope to have a first paper out soon. And what I talk about today will be part of this first paper. So let me maybe just mention something about Motivic integration. Just to review how the Motivic integration was originally defined. So Motivic integration was introduced by Kontsevich in 95 as a geometric analog of p-adic integration. Was motivated by a conjecture by Bartiev on odd numbers of Calabi-House, and then the theory was developed by Denef and Lozer in 99, and then by many other people. There was further developments, and I will mention a few names later on. So let me just review very quickly what it is. So for simplicity, let me assume X is a smooth variety here, and let me denote by n the dimension of X. And so integration will take place on a space associated to X, which is the arc space. So the arc space is denoted by X infinity. So it parameterizes map from a formal disk onto X. And so one way of thinking about how to describe the arc space in fact is a scheme. And a good way of defining it is by approximation from the jet schemes. So this will parameterize jets map for jets on X. So these are just the nth neighborhood of a point of the origin A1. And so there is a truncation map. We give a map going down this way. We call it maybe phi m. And X infinity is the inverse limit under this map. That's one way of defining it. So it is an infinite dimensional object which has connection to valuation theory and singularities of the variety. And so the Motivic integration is defined over the space. And so the first thing we want to say is what are the sets that we want to define a measure of. And the sets are the constructible set of X infinity, also called cylinders, at least when X is smooth. So these are set in the following way. Suppose you start with a constructible set C on some final level, on the jet schemes, and you just take the inverse image, the cylinder, over that. So this will be the set that we focus on. And then you want to define a measure which is defined as follows. So I'm going to use mu for all the measures in this talk. This is in the context of this original definition. So I want to define what is a measure of a set like this. I want to take a Motivic measure. So the idea is that I want to define an element, maybe in the first approximation in the Grothendieck group of varieties. But this inverse image is not a variety because it's an infinite dimensional object. But the idea is that I can use the fact that this looks like a cylinder over the base, and I understand the fibers very well. The fibers are all affine spaces under these truncation maps. So the first approximation, I just think about taking the class of C in the Grothendieck ring, but then I need to make sure that this is independent of the choice of M. If I truncate a little less, I want to make sure that I get the same thing. So I need to renormalize to take into account the fiber dimension. So this is done by multiplying by L to the minus MMs, where L is a class of the affine line. And so this makes sense, well defined. So this is defined inside, you look at the Grothendieck ring of varieties, And then you need to allow these negative powers of L. So you need to localize at L. So you add adjoint L inverse. So this is the Grothendieck ring. So it's generated by isomorphism classes of varieties. There are some scissor relations, which essentially say that if I have a variety Y, and I remove a closed subvariety Z, there should be Y minus Z. And then there is also the product. If I have two varieties, Y and Y prime, I take it, this way. So the fiber product will define the product in this ring. And in general, you can define this by looking at varieties over the field, over the ground field. But in fact, it's more natural, and I will do this later anyway. So might as well just taking what I denote by variety over X, this separated scheme of finite type over X, and look at the Grothendieck ring of that over X. So now L will be the fine line over X, and the product will be a fiber product over X. Okay, so this is a measure on to define Motivic integration. Now the question is, what kind of function we integrate? So functions, they're going to look like L to the minus order of along Z, where Z inside X is some proper closed subscheme. Maybe a divisor, for instance. And you notice that the order along Z is a function on the arc space. So, let me make this right. Z infinity. It takes an arc alpha to the order of contact of alpha Z. So every arc alpha will define same evaluation, and I can compute the order of contact. It could be infinity. For instance, the arc alpha is entirely contained inside Z. Okay. And now we can define the integral. So let me write it here. So I want to define the integral of a space of arcs of a function which is of this form, order of Z, with respect to the measure that I defined before. So the way I want to think about this is that these other functions define, because there's values in Z, so you're gonna have some level sets where this become constant, and I just compute the measure of those level sets. So that's by definition will be equal to Q greater than 0, mu, the measure of the corresponding level set times the value of the function of that level set. So this will be defined inside the Motivic ring, which is a completion of the ring where I took the measuring. The reason is that I need to allow a power series to I need to make sure that this power series converge. So I need to complete allowing the dimension to go to minus infinity. And so what you notice from the definition and from this is that so the arc space has this approximation given by the jet schemes. And if I want to compute the integral of some function, I can approximate the integral by looking at the jet schemes, and that will correspond to some approximation to approximating this series by a finite sum. And then the higher I go in the jets, the closer I get to the final integral. So it might be worthwhile just to see a simple example. If you have if you're not familiar with motivic integration, this is a typical example you want to work out at the beginning. Suppose that there is a smooth divisor on X, and take maybe some integer greater than 1, greater than 1. And then I want to look at the integral over x infinity of L to the minus the order along this divisor, maybe A times D. So there is a big stratum, the complement of D, when the order function is 0. So that one is easy to see that we're going to give me the class of x minus D. And now I need to compute this, the remaining terms of the power series. And when you work out in the in the J schemes, what are how the contact loci, these level sets, how they look like, you see that what you get is something looks like this. So it's going to be the class of D times L minus 1 times L to the minus A plus 1 M. So this is just a computation. And then the idea is that in this completion, I can take the sum here. This looks like a geometric series. When I take the sum and then simplify, what I see is that what I get in the denominator is a class of projective space. So I get these denominators, and in fact, using the change of variable formula and resolution of singularities, I can reduce to computation and look like this, and therefore I can see that in fact these integrals take values can be assumed to take in value on some localization without needing to complete. So the proof of the construction is purely geometric. And to understand these things, use resolution singularity. That's a main tool in this original construction. But I want to mention that there have been several developments, and in particular, some developments use model theory that led to more sophisticated theories. So let me just mention two of them is relevant here. One is Kluckers and Loisel. So this is they introduce something known as constructible Motivic functions. So according to the theory, so this class of functions, which is a little bit more general, and then you can develop a theory in which you have a functoriality, integrals will be given by push forwards. And as a powerful theory, it has a lot of applications. And then another work I want to mention here is the work of Rushovsky. And Kashdan. They define integration in valued field. Let me also mention a related work which is relevant for this talk, is a work of Roser and Sebag, integration. Rigid varieties. So this is a very rich world of Motivic integration, and so what I want to talk about in this talk is a point of view which kind of takes a little bit from all of these different works, so the goal is to use Berkovic space instead of arc spaces to define integration, and And again, so this of course relates to Rogowski-Kashdan integration in value field. The focus in this talk will be on a different setting as we're working over, say, over the complex numbers. But it also relates very closely to the original definition of Motivic integration, with just from a different point of view. And then you also want to relate to Klucker-Loiser in terms of this functoriality property. So again, some of the features that we are looking here, the first thing is that we want to use tools from birational geometry. So we're not relying on model theory, but rather on theorems in birational geometry, which of course has some limits. There are some assumptions on in the setting. But so another thing, property we're looking for is a functoriality, like in Klucker-Loiser theory. Then you want some flexibility, which Berkovic space provide naturally. So for instance, we want to work over the complex numbers, which will be the focus in this talk. But we also want to set up something that can be reproduced also over at least some value fields. And this is something that would relate to Rogowski-Kashdan theory and also to Loiser-Sebag integration on rigid varieties. So again, there's many similarities with various of these other works and analogies. And so let's discuss, and then maybe the last thing I'm saying here will be a blend of Motivic and the base measures. Okay, so let me focus on the case where I fix a ground field to the complex numbers. Okay, so you start with a variety X, variety over K, and to this we can associate an analytic space. And the Berkovic identification that can be thought, I mean, locally on X can be described as a set of multiplicative norm, semi-norm on X, which are trivial on C. And I can think of this as a space of valuations. So I can think about this as pairs of a point and evaluation. Like C is a point in X, and V is a valuation of the residue field. So using this description, I can now focus on a subset where all the valuations, so maybe R valued, the R valuation. So these are all the R valuations.
Tommaso, there's a question in the chat.
Oh.
Dan
yes.
is asking if the semi-norms are in OX.
Well, yeah, you do this on local rings. So for a fine variety, you look at the space of semi-evaluations on the ring, and then you glue them together.
I was just picking. You wrote semi-norms on X. You meant on the ring.
Yes. Yes. Well, I think about really in my mind, I tend to think of this as valuations, and I use the language valuation on X, same evaluations on X. So the birational locus inside here is all the R evaluations of the function field of X. So this corresponds to the case when C is a generic point of X. And then inside here, I'm gonna look at something which is denoted by X val. This is what I call these are the evaluations with center in X. Okay, so if X is proper, then of course these two sets are the same. So integration is really defined on, will really be defined in this space of evaluations. So let's for a moment assume that X is proper for simplicity. Otherwise, there is another space I would have to define. But if X is proper, then there is a complement of this set inside an identification, and the measure I'm going to define it will be naturally going to 0 on the boundary. But in fact, there is an interesting kind of a natural way also to put a non-zero measure on the boundary, which is kind of looking at all the restrictions to the subvarieties on X. But I will not say more about that in this talk. I will just focus on this subspace. Maybe I should say though that if X is not proper, there's no good way of putting, at least from the point of view that we're taking here, there's no good way for us to put a measure on the back side of the space. So all the same evaluations which don't have a center in X. So just like arcspace has an approximation under the truncation maps by the jet schemes, so this diagonal space, at least the space evaluations, and let's focus on that, has an approximation by something called skeleton. Okay, so let me explain this. So let me first introduce a notion of a simple number crossing model of X. Of course, a simple number crossing model is a pretty common notion, but I want to make a couple of specifications in my definition for this talk. So what this is, this corresponds to some model X pi with some boundary divisor D with a map pi to X, which is proper and rational. And I want this to satisfy some properties. So the first thing, I want the divisor D, when I write as sum of the I, to be, of course, it's going to be a simple number crossing divisor. And I want the reducible strata. So di, this is just the intersection of the components in the divisor by the subindex capital I. Okay, so if you blow up more, you can always ensure that this condition is satisfied. Also, I want to make sure that the divisor contains the exceptional locus of pi. So pi, this will contain inside D, the support of D. And then another property is that if I look at the Jacobian of pi, the Jacobian ideal, I want this to be locally principal. So this is equivalent saying that pi needs to factor through the Nash blow up. Kind of, okay, let me just write it this way. Because the last thing I want to say is that in my definition, I want to allow X pi, sorry, I want to allow singularities on X pi away from the support of D. So I'm not looking for full resolution. Maybe there are some singularities far away, and then I resolve some other singularities, and then I have divisor there, and I just call this a simple number crossing model, even though I didn't really resolve everything. This is just useful at the end when I want to interpret the integration as a push forward. Okay, so associated to any simple number crossing model, pi, I can define a skeleton, which I denote by sk pi inside the space of evaluations. So what this is, as I said, this is all the monomial evaluation with respect to the toroidal structure. of the pair x pi d. So if you look locally at the generic point of the strata, and then you can fix coordinates locally in so the coordinate will define the components of the divisor at that point locally. Then I just look at the Monod evaluation in those charts that in respect to those coordinates. So there is a natural retraction from the space of evaluation to any skeleton, either by rho pi. And the space of evaluation can be described as the inverse limit under this retraction. So again, this situation is very similar. It's kind of analogous to the approximation of arc space by jet schemes. But analogous at the same time, we see there are some differences, which has to do with the fact that the Berkovic space has a different way of packaging evaluations that maybe has some advantages. Okay, so
supposedly it would be enough for you that pi would be toroidal rather than simple normal crossing.
Yeah, but probably, yes. For me, it's just simple to work with simple normal crossing models. So the skeleton can be thought as a fan of the dual complex of the divisor delta of the divisor D. So let me just draw a picture. Suppose, for instance, that X is here, this X pi, this is a model, and maybe D has two components, like that. And so if I draw the dual complex, in this case, it's gonna have 3 vertices and 2 edges joined together. Let's see how in this picture the dual complex is gonna look like. And if you just take a fan over that, I think this keep going. So this is how the skeleton is gonna look like. Okay, so there are some points here, which is kind of maybe corresponding to the evaluation around the components. And then there are some more faces. And the faces will correspond to the strata, so to some strata. And more naturally, we to think about corresponding to the open strata. And we'll see this in a moment. Which of course correspond to the faces in the dual complex. There is a point here, the vertex or the origin of this fan, which corresponds to the tree evaluation. So there is maybe let me draw this picture one more time. When I look at the skeleton, and maybe let's focus on one face. Let me maybe look at this face here. So there will be some points on the rays around this face, which correspond to the valuation, this valuation di, maybe this is some valuation of some dj. And then there is a tropicalization map. We send this to the octant positive S, where S is the size of the index set. And I send these valuations, the mark there, to the point of coordinate 1, 1, 0, 0, and so on. So I think about fixing coordinate of an x1 here all the way to xs, sorry, xs here. So what we do is that we have this map and we pull back the back measure, and we rescale it by a function which looks like e to the minus a sub x hat, which I define in a moment, to get some finite volume. Okay. So let me now say what this function is.
Finite volume on what?
Pardon?
Finite volume on what?
Well, so the volume of this quadrant is infinite, right? But if I rescale it by some e to the minus something, I'm gonna make it into something that looks like a finite volume face of a cube.
Yeah.
Okay, so the question is, what is this function? So this function is, this is just a matter. The discrepancy function. Sorry. On the evaluation space. So let me just two properties of this function that are enough to understand here. First of all, this function will be continuous on the skeleton, and it satisfies on all the evaluation, these are evaluation points. So this will just be the order along E, or the Jacobian, call it G plus 1, where for every prime divisor E on any say resolution singularities. So every prime divisor over X, the defined evaluation, which will be some integral point in the skeleton, in some skeleton. And I just want this function to take this value. So it will be just the order Jacobian. If X is smooth, this will be just the usual log discrepancies. Okay, when X is smooth. This is just the usual log discrepancy functions of on Johnson and Mustafa, which in fact maybe trace back to really Farr and Johnson when they define a thinness function on the relative tree. But the point is that, and this may be another aspect, advantage of working with Berkovic spaces rather than arc spaces. The definition I gave on arc spaces, it extends to the singular case, but working with arc spaces in a singular case is a bit more complicated because the structure of the truncation maps is complicated. So it's, at the end of the day, you can still carry through the same definition, but requires some care. But here, once from the point of view of Berkovic spaces, since we go to these resolutions anyway, it makes little difference, and all the singularities from X get absorbed in this function, in this log discrepancy function. Okay. So now I have this in place. So now I can define the measure. So again, I have a similar picture that one I drew before with the arc spaces. I have this space evaluations, and this has this retraction maps to this skeleton space of quasi-monomer evaluations. These are called quasi-monomer evaluations, the element in the skeleton. And so now, what are the sets? This again, we look at like some sort of cylinders. So I look at subsetting set here. And for each as a set, I look at this restriction to the faces. Oh, I forgot to, let me actually add this notation. Sorry, I'm gonna go back up. So every face which corresponds to some index set, I'm gonna denote it by sk pi comma I for the index set. That's a face, a notation for a face. Okay, so, and then I look at this restriction and I ask that restriction will be measurable with respect to the volume that we just introduced. It's the back volume rescaled by this discrepancy function. And then I just look at the inverse image of S inside here. So it's going to be cylinder over S in this sense under this retraction map. Okay, and there's just enough space to write the measure. Again, I use a mu for all measures here. So the definition is that, well, I break things in terms of strata. You know that this is a finite sum. On each stratum, I pick up the class and the Grothendieck ring of the open on each face. I pick up the stratum on the corresponding the class of the corresponding stratum, open stratum of the pair, and now I integrate over this piece of S exactly this volume form, which is e to the minus ax hat dx1 dx. Okay. And so this has a strong analogy. In fact, it's closely related in other settings to the definition of Rujovsky-Kashdan, where they also pick up the Motivic part from the specialization map. In this setting, when we work over a field with trivial norm, and we don't think about specialization, but you think about the center map. And so the center map is going to pick up the Motivic component in this measure.
So Tommaso,
yes,
the matter discrepancy is always strictly positive, even if X is very singular.
Correct, because it's an order. Yeah, exactly. So that's also what ensures that these things are indeed a finite volume. Yeah. So it's
okay.
Yeah, it's zero only at the trivial norm, the pre-evaluation. And the theorem here is that this is well defined. And let me tell you where. So let me introduce a notation for this. I'm going to call it MR sub X. So I look at the Grothendieck ring of varieties over X, but I need to divide by L minus 1. So that's the downside of this. And then I just tensor by R. So the idea is that some of the denominators that we saw appearing in the original motive integration, which is these projective spaces, get absorbed as denominators, numerical denominators, like rational numbers. And then, of course, I can look at this over the real numbers if I want to integrate Lebesgue measurable sets. So, differently from using arc spaces, this requires a proof. I mean, the arc space is really the fact that this measure was well defined. It was a simple consideration once I know the structure of arc spaces, but this one requires a proof. So for this, we use resolution of singularities, or marked ideals to be precise, and weak factorization. So let me give you an idea of the computation and see also why we need to mod out by L minus 1. So there are so resolution of singularity and weak factorization essentially will tell you that is enough to, I mean, first of all, what do we need to prove? The point is that there is a choice here. I'm choosing which model. So the same set here, it could be a cylinder over a different choice of model. Then I just need to make sure that if I choose models differently, I'm not changing the measure. So using weak factorization, I can kind of go back and up and down using just transversal blowups. And that's what we want to do. So the idea is that it's enough to understand transversal blowups. And the simplest case is the following. Is when I have a blow up from a model x pi to a model x pi prime, this is a blow up of a smooth transversal center C, which is not contained inside D. Okay, I mean, in principle, it could be inside D or not inside D, and the simplest case is when it's not inside D. So let me explain the computation here. So let me first draw a picture, space here. So this will be the blow up, and this will be x pi. So this is x pi, and this is x pi prime. So on x pi, maybe I have some divisor, so denoted here by a triangle, and then I have a center C. And the center C intersects the divisor transversely. And then when I blow up the center C, I extract a new divisor, which is fibered over C, call it E. And then there is a proper transform of D, which I call D tilde. And you notice that the fiber of the projection, the fiber will be some P C minus 1 if I denote by C the codimension of C inside x pi. Okay, so now the question is what happened at the level of skeleton? So in the picture downstairs in x pi, I have only one divisor. So the skeleton here is just looks like this, is a one-dimensional fun. So as a one coordinate x, this is your valuation. Now the skeleton of x pi, instead, it looks something like this. So I'm gonna denote this coordinate by x. I didn't really center it very well. Let me actually center better. And I denote the new variable by y. So the fact that C is not contained in D can be seen here by the fact that this is just a projection on the y coordinate. If I blow up something which is inside D, then the projection will be kind of skewed because the valuation, the pullback of D would actually have coefficient in E. But in this case, this is the simplest case. So now let's think about what are the Motivic pieces here. Here I have the class of D. Here I have the class of D tilde. When I remove there is an intersection between the stratum here, which is E intersect D tilde, that I need to worry about. So the vertical part is the section divisor, E, and again, I remove the intersection, just look at the open stratum. And then the two-dimensional face will correspond exactly to this E intersect D tilde. Okay, so that's a picture. And what do we have here? So I can compare this class in the Grothendieck ring. So the first thing I see is that if I just look at the space here, well, this is outside the locus I blow up. So this will be defined the same class, would be minus C. And now when I look at other pieces, I can look at them together, in fact, and just make the discussion a little bit shorter. And so I see that the class of E, because E is a P C minus 1 bundle over C, it will be just the class of P C minus 1 times the class of C. Okay, so now the question is what happened to the integral part. So in the definition, I kind of compare these pieces, but now I need to compare the two integrals. So for that, we just you just need to integrate along the fibers. And so this will give you an integral that looks something like this. Integral from 0 to infinity of e to the minus cy dy, just because c will be the difference between the two discrepancy functions. log discrepancy function. And that gives us 1/c. So now when I put things together, I need to make sure that these terms and this term, they cancel out. So if I maintain a Motivic part, I cannot cancel it out. But that's where the working modulo L-1 does, is that a projective space is the same as C minus one dimensional projective space is the same as C, the number C. So this is the same, yellow. This is the same as C times the class of the curves of the center C. So they cancel out.
Does this sort of determine the integrand that you, how, to what extent does this well-definedness determine the integral that you are allowed to take?
Well, let me actually give you, I don't know if this really answers your question, but I can put a different measure and actually work without having to mod out by L-1. So I can retain those denominators as projective classes. But this requires working with some atomic measures. I don't know if this kind of answers your question. I mean, I don't know if you want to maintain that kind of these Lebesgue integrals and just maybe change the rescaling factor. Maybe that is possible to come up with a different rescaling factor that still work. I don't know that this is extremely natural. This is just a right scaling factor. But again, so the point is that you don't want to mod out by L-1. So as a side note, I can give you an atomic approach. Okay. So remember the picture that we had before. So we were looking at some phase. Let's make it down by this. Oh, sorry. Pi. And then we have this tropicalization of the phase. They went down to R, then 0, yes, okay. And the phase has I here. So what I can do here now in this space, I can look at all the integral points. So this I'm looking at n to the s. And if these are the two valuations were here, then essentially I'm just looking at these integral points here. So I'm gonna add a z in the notation when I restrict the phase to these integral points. So I can forget about all the real valuations. I just focus on, so essentially here, we are focusing on z valued valuations. By this, I really means the element in the Berkovic space are valuation with value in R, and I fix z inside R. So I really fix a normalization. And I look at valuation with value inside z as a subgroup of R. And so if you do that, then you can introduce a following rescaling factor. So again, this will be some a Motivic rescaling factor, but it's essentially you replace E by L. And then you get something which looks like some finite volume. A finite volume, it just means that I can take the sum of all those points and I get something of finite, some finite number, finite quantity. So this gives a Motivic measure. When I look at the space of valuation, I can look at the one which are values inside Z, and this has with values. The measure has values in the usual Motivic ring as a original Motivic integration. So this kind of alternative approach is much closer to the original definition. It is also very close to the work of Klucker and Lozer. Okay. But let me go back to the setting of working instead with the whole space of real evaluations. So let's see what time is it. Oh, I'm running out of time. So functions for every model pi, I look at exponent space f and pi. I want to look at this Motivic ring at the level of varieties of the model x pi, and then I tensor with the space of functions from the skeleton into R. And the tensor here is over the subgroup, the subring generated by the characteristic functions at the strata, where every characteristic function of the strata, or the stratum, get maps on the left side to the class of the open stratum, the corresponding stratum, open stratum. And then I can define now this space just to be the direct limit. There are natural pullback maps, and I can define the direct limit. So an element in here can be represented by some sum or some classes at the level of x pi, tensor some functions, but the function is defined on the skeleton pi to R. So you can fix an R and a pi, and you get a representation like this. And now I can tell you what the integral is.
Are these functions piecewise linear or constructible or anything in particular?
No. So this function, so if you use atomic approach, then you need to put a good restriction on what kind of functions you want to use, and that's reloaded from Klucker and Lozer. But in this case, at the moment, I just look at any real value function, and then I will just ask this function to be integrable, define an integral. So the integral over the space evaluations of a function in nu will be just as well. The function is defined as above, where I look at all the pieces, all the terms in the function, and look at all the strata. Then the Motivic part, of course, will be just the product over x pi of the Motivic pieces. And then this will compute at the level of x, so push forward down to x. And then it will be the integral over the corresponding face. And I put the function inside here. I have this rescaling factor. So one difference that maybe is worthwhile to mention here from the using R spaces is that when we approximate the evaluation space by the skeleton, then we can actually, we don't get an approximation of the integral, we get the integral. So that's maybe, and that's maybe just saying that the way evaluations are packaged in a Berkovic space maybe is more convenient from this point of view than the way evaluations are packaged in the arc space. Okay, so if we do the example, suppose x is smooth and this smooth, and a greater than 1, then the integral of e to the minus the order of AD. Well, maybe I skip let me just say what the output is, so you can compare just a simple integral in between. So the denominators, now, before it was a projective space, but now we get this Euler characteristic. So this will be the projective space using the atomic approach. So in a way, you can say that this point of view actually really recovers the original integration. So let me also talk about the change of variable. So while we need to work a bit harder to prove that the measure is well defined, now the upshot is that the change of variable, it comes for free. Because a birational map will use an identification between the space of evaluations, and then it's just a matter of comparing the two log discrepancy functions. So the change of variable says if G from Y to X is a resolution of singularities, then I can compute the integral of the evaluation space of some function in d mu. That will be the same as the integral of the evaluation space of Y of what, where I put back the function is a map on evaluation spaces, which is just an identification really. And then I just evaluate the Jacobian ideal of G on the evaluation space in d mu. And to be precise, since I'm taking values in the Gaussian ring of the varieties, I need to push forward this guy. Yeah, so that's how the change of variable looks like. So so in the last few minutes, and maybe if it's okay, I take maybe just a couple of minutes. It shouldn't be more than that. I want to talk about functoriality. So this is one of the features of Kruker-Elvazer's work. So, and let me explain how, in which sense we can make a sense of this here. So we look at a category of supernormal crossing models in the following sense. So maybe walk over some base, but let me just tell you what the map between. So objects will be something like simple normal crossings on some variety. And map will be given by a map between the variety we refer to dominant, which induce a map on the simple normal crossing on the models. Maybe there's some simple normal crossing model here. We require a map here. If we call it map G, this we call G pi sigma. And we ask the G pi sigma inverse image of E is contained inside D in the support of D. So using integration along fibers, so first of all, you have an induced diagram on evaluation spaces. There's a map here. And, oops, what happened? So, and there is a skeleton here and a skeleton right here. So I want to define a map going down this way, and there is a natural way of doing this. Well, the skeleton is included inside here, inside the evaluation space, and then I can project and then have a retraction map going down this way. So this defines a map here. And this map is, you can see, we can check is compatible with the retraction. I mean, there is a retraction map going down this way, and that will also give a commutative diagram if I were to replace inclusion by the retraction. So this is a piecewise linear map on these fans, and so we can integration along fibers of this new map will define a push-forward map. On Motivic functions. So by using this push forward, we can enlarge the space of Motivic functions. By instead of taking a direct limit and a pullback, we can take a inverse limit and the push forward. It's very similar in spirit to the difference between you know, Bell divisor and Cartier divisor. Although the push forward does not kill everything that is killed geometrically, so we need to keep that in mind. So there is a caveat here, is that this requires some additional bookkeeping. Let me explain this with a simple example. So suppose there are two models, and the first model, I have a device that looks like this, SD, this XPy. And then what I'm gonna do is I'm gonna blow up a stratum. And so this we're gonna extract a new divisor, which is fiber, over this intersection here. So what happened to the skeleton is that here I have a two-dimensional skeleton, look like this. And when I blow up, the skeleton at the same point, so I've not made the set bigger inside the evaluation space, but the fan structure has changed. All of a sudden, I've introduced array, which is a non-zero measure. But this image here has zero measure. Okay, so because of that, if you push forward, and a function which is identity on the set, but we kill a measure, so we need to remember those things. The idea is that in this corresponding between a simple normal crossing model and skeleton, there's kind of a redundancy when I just think about the skeleton as a set of points or set of evaluations, because I can always take these toric blow-ups and without changing the set. And the upshot, so like in Klucker and Loisel, we have a Fubini theorem. And then we also recover the integral we defined before as push forward to the skeleton, sorry, to the identity of the variety X, which just corresponds to a single point, the point given by the zero evaluation, the tree evaluation. This is why I want to allow the simple normal crossing to have singularity, so that I can do this even if X is singular. Again, this is kind of irrelevant on this point, but yeah, so that shows that in particular integral itself that we defined before is part of this functorial approach. And this again is a parallel to what Klucker is there. Okay, so I think I'll stop here. And sorry it took a few extra minutes in the end. And happy to see if there are any questions.
Are there any questions for Tommaso?
So maybe, did you say more precisely exactly which sets you are allowed to measure?
Yes, I can go back to that. In which, in atomic approach? Or
maybe the non-atomic one.
The non-atomic approach, yes. So all I need to make sure is that this integral is finite. So the set has to be again. So this kind of rescaling is just bringing a quadrant, which goes to infinity, to something which looks like a finite object. So any set in here will correspond to some set in here. And all I'm saying that this is measured in the Legback measure induced by the embedding on this into the plane now.
Okay, so it can be quite general sets there.
Yeah, it's quite general. Yeah. I mean, the point is, yeah, maybe, yeah, okay, anyways. So other questions?
I have a very naive question, but so what kind, maybe it was a bit what you were saying at the beginning, the motivations that you were giving, but what kind of applications do you have in mind?
That's a very good question. So we started writing this without really having one particular application in mind. But we do believe that there are several advantages in working with Berkovic spaces. The fact is that Berkovic spaces, again, is a very flexible theory. For instance, I didn't talk about this in here, but when you work on a relative setting, so let's say over some value field, again, maybe geometric situation, like, over a curve, and then you look at the completion. So, the point is that now you have an hybrid space. This kind of hybrid spaces have already been used before, for instance, by Berkovic itself, in fact, and have been used right now. So the way we define integral in that sense, for instance, is a kind of an average under the normalization of the value of the parameter. And so it fits very nicely in this hybrid space, and then you can put the trivial norm in the central fiber at 0, and then make comparison theorems there. That's one thing, for instance. Another thing that will be interesting is the fact is that you can enlarge the space of functions already. That we enlarged quite a bit, but one thing would be really interesting to do is to understand that if you can integrate functions that come from, maybe say, Veil divisors under some Veil B divisors under some good assumptions, like maybe Neff Veil B divisors. So this relates to questions about the Meide-Collat openness conjecture that has been solved analytically. Maybe this might give a framework. I'm not saying that it will give a proof, or maybe give a different way of thinking about or looking at these kind of properties. It's still not completely clear how to handle, because the Motivic part will get more and more complicated, and push forward does not kill the species. So that's the difference with B divisors. Yeah, I mean, again, so this application. Another thing I think that would be nice to work out is Motivic, the McKay correspondence, just because, unfortunately, I didn't have time to do the last example, but one of the difficulty understanding McKay correspondence using arc spaces is that the maps between arc spaces are complicated, because when you have a covering map on arc spaces is not surjective in a meaningful way. So you need to take roots, but if you take too many roots, then you don't have a map. So you need to break things into pieces and look at one piece at a time. But when you do this from a point of view of Berkovic geometry, it should be easier. That's because the roots are embedded, and in fact, we just look at real value valuations. So you can lift. And in fact, the expectation is that maybe a McKay correspondence might come out from functoriality. You have a kind of a diagram, and you will go from, you push forward one way, and push forward the other way, and they should keep the two pieces in the formula. But we haven't worked that out yet.
Cool, thank you. Are there any other questions for Tommaso?
Tommaso?
Yes.
Could you repeat the application that you have in mind for the hybrid space? I mean, is a way to compare the two different measures, the one that you define at the beginning and the one in the Berkovic setting?
No. So in this talk, I focus on the case where the ground field has a trivial norm, like C, for instance. For instance, let's say I work over C double bracket T, something like this. So on some setting where I have now some t-adic evaluation on the field. And so I can we can reproduce this definition in that setting. And the funny thing is that typically when people work on a setting like this, you fix a evaluation on the field. And that's it's like fixing a normalization of the parameter, the T in my discussion. So they correspond to some slice of a bigger Berkovic space, which were allowed the evaluation of T to change. So our definition actually fits better when you allow T to vary. So there is a natural interpretation which whatever measure we define, or whatever integral we define, would not be the integral over any of these Berkovic spaces over the value field, where we cannot average, because the Lebesgue measure will depend on the summarization. So you average it. But by doing that, you're already working on some sort of an open set in a hybrid space. You just keep going a little more, and you get to the trivial norm. You added one point on the base, you added one fiber there, and that's an hybrid space. And now you just look at that, and then for instance, if you really work over, say, you start from a model over a curve, over a field, and assume all the results you need to assume a resolution singularity, say, then you can compare. Then you have actually three integrals, and they have an integral over the value field, you have an integral over the residue field, and then you have an integral over the big field regarded with the trivial norm. And then there is you get automatically a formula which relates these three integrals, and then you get some sort of a transfer in one direction, for instance, about integrability. So these are kind of things that come up naturally there.
I see. Thank you.
Yeah.
All right, maybe we can all thank Tommaso again.
Thank you so much.
Thank you very much.